So we have a few slides in lesson 5 to finish today. For example, this is the slide about non-collinear configuration of second harmonic intensity autocorrelation measurement. The microsecond interferometer is slightly changed. So you can see we use only one beam splitter, and we need a mirror in place of the second beam splitter. And in this way, the two pulse replicas propagate in parallel with each other, but along different axes. 所以这没有走在一起，平行但是没有走在一起。Then we can use a lens to focus the two beams into a thin crystal for second harmonic generation. Then what do we have? You can easily identify there will be pulse 1 and the pulse 2. They are just proportional to the square of two individual pulses. Like pulse 1 is the second harmonic due to A of t minus tau, this single pulse. And the pulse 2 is the second harmonic of the field A of t. Okay? And these two pulses can be blocked by an iris. We do not need these two pulses. And between the two output pulses, there is a third one, pulse number 3 here. Okay? The electric field, second harmonic electric field, is the mutual product of the two fundamental fields, A of t and A of t minus tau times e to the minus j omega 0 tau. Okay? The mutual product now is separated from individual square. Okay? So just like the mathematical formula, a plus b parenthesis square, you should get 3 terms, a squared, b squared, and the 2ab, right? Now, a squared and the b squared are blocked by an iris. Only the cross product term, a times b, is preserved in the third beam. Okay? So we just use a slow point detector to measure the second harmonic energy of the third beam. Okay. Then mathematically, we should get this. Okay. Now, the I sub IA function of tau is proportional to the second harmonic energy of the third beam. And what is the energy? You have to integrate for the intensity, which is absolute square of the field, right? And by inserting AC of t with this formula, you can see the output is directly proportional to I of t times I of t minus tau time average, which is the G2 function we desire. Okay? So this non-collinear configuration can directly give us the G2 function without the requirement of post data processing. Okay? We do not need Fourier transform. We do not need low pass filtering. Okay? This is the G2 function. Okay? Any question? Then, single shot configuration. Sometimes delay scanning is inappropriate, especially when shot-to-shot fluctuation is non-negligible, such as the output of laser amplifiers. Okay, because the pulse energy could be very large, the shot-to-shot fluctuation could be non-negligible. In this case, if you need to scan the delay, like what we have seen before, the measurement could be inaccurate. So people think about, is there any way we can measure the autocorrelation trace with just one shot? Okay. And it turns out that This is possible. Just use the non-collinear configuration as I shown you in the previous slide. Now you have the two post replicas are closed. Say this is the blue one is post 1, the red one is post 2. They are essentially identical. Okay? But if you close these two beams, remember in reality, laser beams are of finite cross-sectional area. They are not plane waves, right? 它们一定会有有限的这个光束的直径。Okay? So I use the two parallel blue lines to illustrate the finite beam size of post 1. Okay? So you can imagine when post 1 hits the plate or the SHG crystal here. When the blue pulse hits the crystal, the red pulse should be here. Okay? So you can imagine at this point, blue pulse leads the red pulse, right? When the blue pulse peak hits this position, the red pulse is still here. So it takes a further propagation time for pulse 2 such that its peak can hit the same place. Okay? So at this position, pulse 1 leads pulse 2. But if you observe another position like here, things are reversed, right? Pulse 2 hits this position and the pulse 1 only travels here. So it takes a longer time for pulse 1 to hit the same position as pulse 2 did. Okay? So at this position, pulse 2, the red one, leads pulse 1, the blue one. So you can imagine across this translation, this lateral direction, different x positions actually map to different timing. Okay? From pulse 1 leads pulse 2 to pulse 2 leads pulse 1. So the delay tau could be from negative to positive. Okay? Probably at the middle, it's the zero delay position. If this is true, then you can directly capture the G2 function by a detector array. Because at different lateral positions, different pixels can record the corresponding second harmonic energy. So the energy distribution along the lateral position is directly the G2 function trace. Okay? So even with a single shot, you can record the entire intensity autocorrelation function. So this is so-called single shot configuration. Single shot IA measurement. Okay. Any question? Okay, but maybe we need to consider some practical issues if you try to implement single shot configuration. For example, how do you determine the range of delay scanning, delay window? Now we do not need to scan the delay because within one shot, everything's there. But what is the delay window size? 你有多大的 delay 范围可以用这个架构实现它 Of course, this is controllable. Okay? For example, if you cross the two beams with bigger crossing angle, you can modify the delay window size, right? Or you can control the beam size of the two beams. You can control the delay window as well. So it's up to your experimental conditions. Okay? You have to know what is the pulse duration roughly in advance. Okay? So you can so that you can determine a proper delay window size to accommodate the G2 function, right? We know the G2 function width is in close relation with the post duration. If you have a long post duration, you need a big delay window to accommodate G2 function, okay? Then you can determine what is the bin size, what is the closing angle you need to use. 如果不考虑这些实际的问题，你可能就是做了这个实验，你只得到一部分的 G2 function because the window size is not big enough. 那 usually window size is in conflict with the time resolution. Okay. If you have a very big window size and you have the same pixel size of the detector array, you may have a worse temporal resolution. In that case, some fine structure of your G2 function can no longer be measured. Okay, so you have to roughly know the parameters of the unknown pose in advance, such that you can balance the window size and the time resolution to establish an appropriate setup for that purpose. Okay, any question? Okay. But if you observe this picture, you might have some question about the previous page, because here we use the non-collinear geometry as well, right? So what would be the problem of this picture? 你用一个 non-collinear 的架构来做，这个其实是 multi-shot. This is not single shot. This is a multi-shot intensity autocorrelation measurement. 你用这个架构会发现什么问题？ According to the next page, we know after you use non-collinear geometry, the delay tau is not a fixed number, not a precise number, but a range of different delays, right? So that means whenever you use a non-collinear geometry, when you talk about tau, it's not just a single number, but a range of slightly different delays over there. Okay, so when you try to measure extremely short optical pulse by this setup, it would be problematic. 当你的脉冲带侧脉冲宽度太窄了，窄到什么？你这个 delay 的不准确度已经跟带侧脉冲宽是接近的。 那这个量测就会非常不准确。Okay, so that's why if you try to measure extremely short pulse, people tend to use collinear geometry instead of non-collinear one. Although there are some advantages you can earn by using non-collinear geometry. Okay. Then. Actually, there are other nonlinearities can be employed for pulse measurement, not just second harmonic generation, although we use second harmonic generation as example. Okay. For example, you can use third harmonic generation for intensity autocorrelation. Everything is the same except that you replace the crystal. Instead of doing SHG, now you are doing THG, third harmonic generation. And the detector is used in measuring third harmonic energy as a function of delay. The difference is now you can have correlation functions of higher moments. Previously, if you use SHG, you have second order nonlinear functions. Now, with the employment of third harmonic generation, maybe you can measure something like this. Average of A of t times A of t minus tau complex conjugate parenthesis cubic. 这是3阶的这个相关函数，你就可以透过这样子的 measurement 得到。 那你如果2倍频，你没有这个，你最多是平方嘛，这个我们看过。OK， so if you use higher order nonlinearities, you can have higher order correlation functions. Okay. Or you can use another nonlinearity named two-photon absorption, or TPA, of semiconductor photodetectors, just like this figure. Okay, this is energy diagram. The band gap is too large for a single photon absorption, so H times nu is not sufficient for transition from valence band to conduction band. But if you can combine 2 photons simultaneously, 2h nu is big enough to make this transition. After that, the electrons can release back to the valence band, and there is photocurrent that you can measure by an emitter. Okay? And it turns out that the photocurrent is proportional to the square of fundamental power, which is very similar to second harmonic generation effect. Okay? So with this simple configuration, you can also measure intensity autocorrelation. Okay. But there are pros and cons, advantages and disadvantages. What are the advantages of using TPA? First, it's very compact and economic compared with second harmonic generation based setup. Why is it compact? Why is it economic? You can compare with the SHG setup. Okay, maybe I use the non-collinear geometry as an example. This is the setup for SHG-based intensity autocorrelation. If you replace the crystal by a semiconductor photodetector for TPA, so crystal can be replaced by a PD. And usually, crystal is very expensive. Photodetector is relatively cheap. Okay, so you earn something by this replacement. And beyond that, you know, after SHG, you need a slow point detector to measure the second harmonic energy as a function of delay, right? But in the geometry of two-photon absorption based autocorrelator, we do not need an independent point detector because the PD itself is already the detector. So actually, it combines the crystal and the detector together. You just use a piece of PD. 所以它省下很多的 cost. Okay. Another advantage of TPA-based autocorrelator is the setup is polarization independent. That means you do not have to pay attention to the beam polarization. Whatever it's vertically polarized, horizontally polarized, tilted polarized, or even elliptically polarized, the response is essentially the same. But if you use second harmonic generation, polarization state is critical. You have to make sure your polarization is precisely aligned. Otherwise, you will have zero SHG crystal at all. Because the second harmonic generation process is highly polarization dependent. Okay. 所以你又可以省下一些这个 maintain 或者是 polarizing 的 laser beam 的成本。基本上这个东西很好用。But there are some disadvantages. For example, the setup is always collinear. No non-collinear geometry. Okay? So you will always, the autocorrelation trace always has background and the fringes. If you use second harmonic generation, just like what I have shown you before, it's possible you have background free and fringe free autocorrelation tracks if you use non-collinear geometry, right? But it's impossible in TPA. It's always collinear. Besides, it's less sensitive than SHG. Okay, the two photon absorption scheme, you need higher input power to have sufficient signal-to-noise ratio for this measurement. The record is 10 to the minus 4th milliwatt square if you use two photon absorption. And in our experiment, the number can be as low as 10 to the minus 9th milliwatt square if you use second harmonic generation. So the sensitivities differ by 5 orders of magnitude, which is a lot. So if your signal pulse is very weak, maybe you cannot rely on TPA. You need second harmonic generation. 所以简单的说，如果你的 laser power 很充分，那你也不在乎有 background 跟 fringe， 那 maybe 这个 TPA 是一个简单可行的方法啊，又便宜啊，又简单。Okay, that's it. Some questions you might need to be able to answer up to this point. First, what is the time bandwidth product of a transform limited Gaussian pulse? Do you still remember the number? 0.441, great. It's a very useful number. Okay. Second, why does field autocorrelation function, the G1 function, only give the power spectrum? Can you prove it? Okay, I show you the detailed derivation process in the slides. Maybe you need to review it. Just change of variables, switching the order of double integration. Usually you can get the result. Okay. Third, what can we know and what can't we know from intensity autocorrelation function, G2 function? What can we know? What information could we get from G2 function? Why should we do the G2 measurement? 一开始我为什么要做这件事？我想知道什么？你量这个 G2 的时候，你是想知道什么事？忘记了？真的忘了吗？这个大概是你进了超快的相关的实验室，你要做量测，一开始你就会做这件事。那你知道为什么要做它吗？ Yes, you just want to know what is the pulse width, but roughly, we just need an estimation. Then you can do that. Okay? But what can we know from the G2 function after we measure the G2 function? What information could we don't understand yet? The precise pulse width, we don't know. The shape of the pulse, we don't know. The chirp rate of the pulse, we don't know. So basically, we have very limited information from the G2 measurement. Okay. 那数学上到底，刚刚讲的是很笼统的。数学上到底这个 G2 告诉我们什么事？其实我在 slides 里面有给你们分析过。We know 25% of the pulse information because we only know the power spectrum of the light intensity function, I of t, right? Whenever you talk about I of t, you have already sacrificed 50% pulse information, the phase in the time domain is already sacrificed. Plus, we only know its power spectrum, so we only have 50% of that piece of information. So that's why we have only a quarter of the pulse information at best from the G2 measurement. It looks very slim, but the quarter of pulse information actually is usually important because it's about pulse width. It's related to spectral phase, okay? Related to, but not equal to, okay? Okay, the fourth question, what is the deconvolution factor of a transform limited Gaussian pulse? You have to remember the definition of deconvolution factor first. What is the deconvolution factor? The ratio of two numbers. What is the numerator? What is the denominator? 分子是什么？什么宽？这个的宽度，这个叫 correlation width。What is the denominator? 分母。什么宽？脉冲宽 delta t. The ratio is defined as deconvolution factor. And what is the number if you are talking about transform limited Gaussian pulse? Good. Square root of 2, 1.414. Okay. This is also a very useful number in the laboratories. Last, how to tell a continuous wave noise or noise burst from the intensity autocorrelation measurement. What would you see when your optical signal is actually CW noise or noise burst? Say, what is the IA function of a CW noise? It's a flat? No, it's not flat. In addition to a flat background, you have a noise spike, okay? And the width of the spike is only the inverse of your bandwidth, okay? So it's nothing about pulse width. Okay. How about noise burst? So instead of a flat background, now you have a pulsed background. And that background or pedestal is related to the noise burst, the average waveform of noise burst. 就整个宽的这个，你上面有很多跳得很快的 noise， 把它平均掉之后，那个东西的 correlation width 会变成你的那个底座。然后上面还有一根细细的 spike， 那就是 noise 的成分所贡献的。